And let's try to do this together. Okay, so what we've got is a river, okay, and then we've got a house, and then we've got the house on fire. Got the house on fire, and we've got somebody whose house this is. So that person, what he's going to try and do is, it's an old puzzle, so in the old days they didn't have any, taps or anything, so really to get some water to extinguish the fire, you have to first go to the river, get some water, and then run back to the house and extinguish the fire. So we've got a river here. So what's the best way of doing this, right? So obviously you want to get to the river as fast as possible, and then back to the house as fast as possible. So what's sort of considerations? How would you do it?
You'd probably move so you're the closest you can be, like in between the river and the house.
Something like this, yeah. I mean, okay. Let's just do a couple of. Wait, I'll do it this way. So there's my scenario. So first thing is, so here we want to somehow get to a point somewhere here and go back. I mean, one consideration is really if you ever really get into a position like this, it's probably better to just do something than to stop thinking, because by the time you finish thinking, the house might have been burnt out. Although you've come up with the optimal solution, right? But since we can kind of, do the thinking now, you might be able to apply what you figured out later in a real life scenario. Anyway, so I mean, we could go like this, right? So we somehow have to get to the river, and then we'll take our time, and yes. So is this going to be the best solution?
No.
So how can you improve it straight away?
Take a direct path.
Take direct paths, right? So I mean, shortest connection between 2 points. I mean, so he's going to the river here somewhere. It's definitely not going to be. We can definitely improve this by replacing these curvy bits by straight things here. Right? Okay. But then there's lots and lots of different ways in which I could go like this. So I could go like this, for example, or I could go like this. That's always going straight to the river and back. Right? So always going straight to the river and back. Now, one question is there going to be an optimum here? Is there also going to be a shortest way of doing this? Well, you can think about it, right? I mean, if you're heading out really, really far, so really, really far there and back, we can actually make this path that we're taking arbitrarily long, right? So if you're heading to this point or to kind of infinity, then the path will get infinite long. The other way also. In between, it's definitely shorter. Somewhere there should be the shortest way, right? Maybe there's a couple of different shortest ways, could be, but there should be at least a shortest way. Right? So one of these guys should be a shortest way. There could be many. So which one is the shortest? So which one is the shortest? So where do we have to put this point? Where do we have to put this point to make it shortest?
Would we have to consider the extra load when we pick up the water? So you might drive further first and then shorter second?
Good point, yeah, good point. Well, let's just disregard this. It actually does become important for a different problem. It's the lifesaver problem, where you have got somebody here on the beach and somebody kind of drowns here, and then you want to get there as fast as possible. And basically, I mean, the way you would initially do it is just go in a straight line. However, once you hit the water, you're actually going to go slower. So this is not the best way of doing it. The best way is somewhere like this. We kind of equal out things a little bit. And actually what the real lifesavers do, well, maybe we're going to talk about this a little bit. So there's kind of an extra load kind of thing coming in. So we could actually factor this in eventually. But let's just stick with, just going there and back. So basically we want to minimize that path here, okay? Minimize that path. Okay, so actually this scenario he gives a clue. So what we'll do is we'll just have a look at the opposite side of the river. So that's a certain distance here. We'll just go to a certain distance over here, and there we'll put a ghost house. Okay, so we'll put a ghost house here. And then, well, if you look at the ghost house, and the ghost house was on fire, what would be the best way or the shortest way to get to the ghost house? What would be the shortest way to get to the ghost house?
Straight line.
That would be definitely a straight line. So there's no question. That's the best way to get to the ghost house. Okay. Now comes a bit of a trick. So the trick is, let's have a look at this path here. So we go on a straight line towards the ghost house, and then we'll actually turn towards the real house and go like that. Now if you compare the lengths of this path with the lengths of the path to the ghost house, what can you tell me?
That'll be equal.
They will be exactly equal, right? So they will be exactly equal because, I mean, they share this bit here, right? So they share this bit, right? And this thing here, well, basically, when I fold over, they fold onto each other, so that they're equal, right? So they're equal. So this distance here is exactly the same as that distance here. Now I claim this is actually the best way of proceeding. So this is the shortest way in which you can go from this point here to that house that's on fire. And can you see why? Can anybody tell me why this is the shortest connection? Okay? Why is this the shortest connection?
If you take another path to the river and then go to the ghost house from there,
Yeah,
it would be longer
Yeah.
because you're not going in a straight line.
that's right.
And if you were to flip it back onto the other side, the distances would just longer.
That's right. That's right. So if you actually look at any other path, so there's one possibility that could be the shortest, but maybe that's also that's the shortest, right? So, but we can really easily that this one is going to be longer than our candidate. Why is this longer? Because we can take this segment here and flip it back, and when we flip it back, it's actually going to go through the ghost house, right? So this path here is exactly as long as that one here. And which one is longer? Well, obviously this one is longer because it's not going in a straight line. And we can do the same sort of thing with any other path we might want to look at. So for example, if we go like this, and we want to know, well, which one is shorter, the black one or the red one? Right? Well, the red one is exactly as long as if we went from here to the ghost house. But then it's clear that red is longer than black here. But since black is the same as black and red is the same as red, then this black is also shorter than that red. Okay? So is that clear? Is that clear? So basically what we've shown is a shortest path has to be of this form, straight to the river and then to the burning house. Okay? So that's the first stage. First stage, you have to show that it's of this form. And the second stage is we show that among all those hooky paths, this one that goes kind of via the ghost house is the shortest one. Yeah? And we do this by comparing it to any other possibility. Any other possibility is longer. Now, you can ask questions. As I said, one of the homework assignments today is going to be to reconstruct this. Right? So I'm going to ask you, there's the house on fire, there's the guy, there's the river, find the shortest solution and make an argument why your solution is the shortest one. Okay, so that's going to be one of the things. So now you can ask questions. If you haven't understood something, now is the time to ask. Otherwise, we'll keep on going with something else. Everybody happy with this? Yeah? Cool. Okay. Right. Now we can stop.